So now we're going to move on to applying some of our concepts from previous units, specifically ideas like continuity and asymptotes. So in example 2, so in this example above, let's scroll up to this example. Notice how our domain was negative infinity to positive infinity. So there were no x values that I could plug into this function to make it undefined. Quick refresher, remember that the domain is the set of x values for which f of x is defined. So f of x is undefined when? We're looking for a few things. When, 1, we have a negative inside of an even root. Number 2, when we have a negative or 0 inside of a logarithm. And number 3, when we have a 0 in the denominator. All right, so these 3 things are going to give us a function that's undefined. Now, quick refresher on horizontal asymptotes. Horizontal asymptotes occur when the limit as x approaches positive or negative infinity of a function equals L. So what that means is that when we take x to approach positive or negative infinity, and we get a constant as our limit. So when our limit is a constant. All right, so an example of this is if I have the function f of x is equal to 2x squared over 3x squared minus x. If I want to find out if this has horizontal asymptotes, then I'm going to take the limit as x approaches. Now I'm going to try positive and negative infinity. So let me take this as x approaches infinity and as x approaches negative infinity. And so what I'm going to do with this is that I can see that if I plug in infinity, this is just going to be a numerator of some form of infinity and a denominator of some form of infinity. So as x gets bigger and bigger, both my numerator and denominator are going to get bigger. And so what we said we did is we divided everything by x to the largest power in the denominator. So x to the largest power in the denominator is x squared. So let's divide everything by x squared. So we get 2x squared divided by x squared all over 3x squared divided by x squared minus x divided by x squared. And now we can simplify these. So my numerator is just going to be a 2. In my denominator, I've got a 3 minus, and this will simplify to 1 over x. So I know that as x is approaching infinity, this fraction is going to get really, really small, and I'm going to say it's going to approach 0, finally giving me a limit of 2/3. Now as x approaches negative infinity, I'm not going to rewrite this. I'm just going to say that I'm going to get the same exact thing when I divide everything by x squared. And here's what I'm thinking. I'm going to simplify it the exact same way. And if I plug in negative infinity into this denominator of this fraction, this term's still going to go to 0 because a 1 divided by a really, really big negative number is still going to be really, really small. So in the case of these polynomials, my limits aren't going to be different. The thing that might differ, though, is if I have a limit as x approaches e, because as x approaches e to the positive infinity, that number is going to get really big. As x approaches e to the negative infinity, that number is going to get really close to 0. So I could say, because horizontal asymptotes have the equation y equals something, that this function has a horizontal asymptote at y equals 2/3. This would be that horizontal asymptote. Okay, Review of vertical asymptotes. Vertical asymptotes occur where the limit as x approaches a from the right or the left is some form of infinity. And I know this is going to happen when I have a function. Let's take, for example, the function f of x is equal to 1 over x minus 2. If I'm just looking for vertical asymptotes, I want to find the x value that's going to give me a constant divided by 0. And I'm thinking, what can I plug in for x to get a constant divided by 0? Well, if my denominator x minus 2 is equal to 0, then I can bring that 2 to the other side and I get x equals 2. So let's just do a quick check of that. What is the limit as x approaches 2? And let's do this from the left. And the limit as x approaches 2 from the right. Well, I've got this function 1 over x minus 2. 1 over x minus 2. Now when plugging in 2 gives me 1 over 0, I know it's going to be some sort of infinite limit. And this is where I'm going to think about a test point. So I'm going to think, if I plug in, let's see, 2 from the left, if I plug in 1.9, I'm just looking to see if this is going to be a positive or negative value. So I've got 1, which is positive, divided by 1.9 minus 2 is negative. So this is going to be a limit of negative infinity. From the right, if I plug in something like 2.1, my numerator is going to be positive. My denominator is going to be 2.1 minus 2, also positive, and so this is going to be positive infinity. And so I've got this vertical asymptote here because I have limits of negative infinity and positive infinity. And if I find out which one's negative and positive, the added bonus of that is that I can find out which way this curve is going, because remember, our ultimate goal is to sketch this curve. And so I've got a vertical asymptote at x equals 2. Now, let's consider the domain as well as the asymptotes of the function before using the first and second derivative tests. So this will just give us more information about our function so that it's easier to sketch. We can also look at the x and y intercepts. Remember to find these intercepts, so to find the x-intercept, you're just plugging in a 0 for y. To find the y-intercepts, you're just plugging in a 0 for x, as well as any symmetry the function might have. So let's talk about the symmetry. If f of negative x equals f of x, so if I make all my x's negative and I get the same exact function, then the function is even, meaning it's symmetric about the y-axis. Let's take, for example, the function y equals x squared. Well, I could write this also as f of x equals x squared. And here's what the symmetry tells me. It tells me that if I plug in a negative x for x, this is going to be a negative x squared, which is just x squared. That negative is going to be squared, making this a positive. You see how f of x, which is x squared, is equal to f of negative x? Well, that means that this is an even function. This is an even function and it's symmetric about the y-axis. And we know what that parabola looks like. It looks something like this. Completely symmetric. So I could fold this graph over on itself. Notice that I am symmetric about this y-axis. So if I drew a vertical line down this graph, both sides would mirror each other. Now, noting any symmetry in our curves is going to be great because it can actually cut the work in half for us when we go to sketch those curves. Okay, what about an odd function? So an example of this would be y equals x cubed. Now I can write this as f of x equals x cubed. If f of negative x is equal to negative f of x, then the function is odd. So let's plug in negative x for x. So f of negative x is equal to negative x cubed And I know a negative cubed is still a negative. This is just negative x cubed. Notice that f of negative x is just the negative version of my original function. So this is just negative f of x. By plugging in that negative, we just negated the function. We just flipped the sign of the function. And this is what this tells me. It tells me that it's symmetric about the origin. Let's see what this looks like. So I've got my graph. Remember what x cubed looks like. It looks like something like this. Now, what this means by symmetric about the origin is that if I rotate one half of the curve 180 degrees, I can form the other half. So if I take this bottom part right here, if I kind of imagine I'm splitting this curve at the origin, and I take this bottom curve and I rotate it up 180 degrees, it will exactly trace over this first curve right here. So that's our odd function. So next, we're going to use these ideas along with our first and second derivative tests to sketch a graph that's a little bit more complicated.